Okay. Um, so I want to do this a little bit differently. I want to answer this a little bit differently now than I have previously. Typically, when I've hosted Amber Book, I've given like a short version of the answer and then talked about the rationale. But I think I'd like to not really do that. I think I'd like to talk about the rationale first, and then have you return to the question yourselves. Apart from the only thing I'd like to say is that they give you, in typical NCARB ARE question style, they give you a little bit more information in the question than is actually relevant. So don't doubt yourselves with that. They've given us some information about the 2200 degree days Fahrenheit, which we don't, that's not relevant to this particular question. What's relevant for this question is where the, just to read the table, where the minimum footing depth is located. So this is the table, this is the column that, or the, yes, the column, oh my gosh, rows and columns that's most relevant to us. The other stuff isn't as relevant. Anyway, so what I want to talk about is frost and foundation walls, and yeah, our footings and foundation walls. And I'm going to start by covering some principles here, some basic principles, and I'm going to do that by showing you some images. But how am I going to show you these images? Let's see. I'm going to look at, forgive me, I'm usually a little bit more organized. This, by the way, is a preview of the topic I'm going to cover on Instagram, Building Science Fight Club, this week. So if you forget any of it, you can come back on Saturday to my Instagram feed, and you'll get this in sort of, you'll get what I'm about to show you. You'll get there. Okay, so the first thing I want to show you is this, and I'm going to adjust my screen so that you can see that a little bit better. Okay, so what we're looking at here is a conceptual drawing of sky and soil. And in wintertime, pretty much everywhere, the air is going to be cold, or at least colder. And the ground is relatively warm in winter. It's often relatively warmer than the air. So when we get our coldest temperatures in the Arctic, in Canada, in Toronto, where I grew up, in Chicago, in Minneapolis, think of any cold places, the air can be extraordinarily cold. But the soil in those same cities, those same extreme cities, is not as cold as the air temperature, right? And that's pretty intuitive for a lot of us. And down here, or the temperature of the soil underneath your slab for your house or whatever building you're designing, ends up being pretty close to the average temperature for the whole year of that city. So not the average high or the average low, but just the average temperature for the whole year. And that's because the Earth acts as kind of the ultimate thermal mass, or the original thermal mass. And it's sort of like a battery, where it experiences heat gain in summer and heat loss in winter, and it all averages out to about the average air temperature for the year. And what that means, though, is that the ground is, when it's warmer than the air, the ground will experience heat loss. Sorry about that. It'll experience heat loss to the sky. And the heat loss is going to be greatest near the surface, right? The part that's adjacent, the cold. And so this soil near grade will end up freezing. If the climate is cold enough, this area will freeze. And we call the frost line the dividing line between the soil that freezes and the soil that does not freeze. And there's actually where the location of the frost line is specified by the building code in whatever jurisdiction you're building in. And there's also a safety factor, right? It's not the frost line, obviously it changes, right? So earlier in the season, maybe it's a little bit closer to the top here and then it goes lower. But the frost line that we designed for is a worst case scenario plus a safety factor. So this is the main principle. And I hope that this is intuitive to you. Probably you haven't really thought of it that much before, but now that I'm presenting it to you in this way, it should seem fairly intuitive, in line with what you would imagine to be the case. So cold air in winter, the ground is warmer than the air, and we experience heat loss upward. Okay, so far so good here. The second thing I want to talk to you about is not totally relevant to the problem, but we're going to take a bigger picture approach with this. And that is this, that when we're talking about heat loss through a slab, don't worry about the stuff at the end there. We're going to talk about that. Heat loss happens in a radial pattern, meaning that the majority of the heat loss is at the perimeter, not in the field of the slab. It's mostly at the perimeter. And that should sort of jive with what I just showed you, right? That should be kind of consistent, because the temperature of the ground here is milder than the temperature of the ground here, and much milder than the temperature of the air. So we've got colder temperatures here and warmer temperatures as we go down. So if you were to sort of see the pattern of heat loss, it would be in a radial pattern. And that means that insulating the sides of your slab is actually more important than insulating underneath your slab. Now, we like to do both because even though the temperature of the ground, it tends to be warmer than the temperature of the ground here tends to be warmer than the temperature of the ground here, it's still cooler than we like for comfort reasons, right? So if the temperature of the soil here is, let's say we're talking about a basement, if it's 50 or 60 degrees, that's not freezing, but it's still not very comfortable for us if we're heating the inside space and we're walking on this floor. We want to keep it warm. So anyway, but keep in mind that the perimeter is where stuff really counts for heat loss. Now let's talk about an actual building. Let's talk about a building with a foundation. And I want to show you a typical foundation, not, typical. There's lots of variations on this, but typical-ish. And that is going to be, hold on, here. So let's see if I can show you most of this. So when soil freezes, it expands, not unsurprisingly, right? Because water expands. We know that from probably elementary school. And the expansion will occur in the direction of the heat loss. So that first image I showed you with the arrow going up, heat loss going up, the direction of the expansion also goes up. So now when we're looking at a typical footing detail, we want to locate, or a foundation wall detail, we want to locate the footing underneath the frost line. So that should make sense, right? But I sort of knew that rule, but the physics kind of helps because I didn't understand, like, okay, well, the footing needs to be underneath the frost line, but doesn't it matter that the foundation wall is below grade but above the frost line? Like, isn't whatever bad thing we're protecting the footing from happening to the foundation wall also? So like, isn't that going to be a problem? And what I didn't understand was that the direction of expansion happens in the same direction as heat loss, upwards. So we've got this upwards force, up pressure. And what we want to do is make sure that the thing that our building bears on, the footing, is below, so that doesn't, below the freezing line, so that we don't have this upwards push against our footing that wants to lift our building up. So this is an upwards force, and it doesn't matter as much when we've got in the same way anyway, when we've got a concrete foundation wall, we don't have the same vertical, we don't have the expansion. Now we do have some, we have, remember that radial pattern, we've got some pressure in this direction, and sometimes different kinds of foundation walls are more at risk of damage, like block foundation walls or rubble foundation walls than concrete. But for the most part, this is what, don't worry really about that. That's sort of off topic. This, for the most part, is just fine for our purposes, right? So that is why we do things that we do the things that we do with respect to putting footings below the frost lines. And the local code will tell you where the frost line is, and you just put the footing below it. Pretty simple. Incidentally, this is also kind of why we do basements in cold climates, right? So depending on where the frost line is, if we have to dig down that much anyway, I mean, we may as well have a basement. Now, that's not what I'm showing you in this detail. I'm showing you a typical foundation wall with a footing below this frost line here, but basement details are really similar. So we want the footing, if this were a basement instead of grade, we would want that to be below the frost line as well. And if we're going to excavate this much, maybe it's worth it for us to just go a little further and end up with an actual basement with occupied space or storage space or whatever. So we rarely see basements in warmer climates, but in colder climates where we're dealing with this kind of heave issue, then often it makes sense to do a basement. But before we move on from here, I want to look at a couple other things with respect to the way this particular slab is insulated while we're at it. So you'll notice that we've got insulation under the slab. So that's pretty intuitive. And then remember we talked about heat loss with slabs being in a radial pattern. So we get a lot of heat loss at the perimeter here, a ton of heat loss at the perimeter. So we've got this little vertical piece here that protects our slab, which is great. So that's also fairly intuitive, I think. What's this about, right? What's going on with this? So it's the same principle. We're still reducing heat. We're still reducing heat loss in this radial. This isn't about insulating our foundation wall. This is about insulating our interior. So having the insulation here still reduces it interrupts that radial pattern for our heat loss lines. So this ends up actually being quite helpful. And if you were to put this in perspective, let me show you, oh no, this one. So this insulation ends up being about comfort and energy efficiency, but this ends up being more closely tied to comfort, and this is more about efficiency. If you wanted to, if you cared, I mean, you should do both, but if I could only do one and I cared about efficiency, I'd insulate on the vertical. If I cared about efficiency and comfort, I'd make sure that I added this piece, which might not be as intuitive. And now when we talk about it, I guess I said this in the wrong order here. Now put a pin in that. When we talk about a shallow frost protected foundation, we can move our footing above our frost line. So we've put it up here above our frost line, and to protect us from the heaving from the soil, we can put insulation horizontally here. And this lets us locate the foundation above the frost line. And it might help to think of it another way. Essentially, this insulation, we're insulating the ground, and we basically move the frost line to up above it when we're adjacent to the building. So it lets us have a shallower foundation. And that might be helpful to us if we have soil, like in the question, that is inhospitable to going down further. It maybe would be very expensive. So it might be a lot. We're not interested in having a basement at all. So this might be a nice option for us. But it's helpful to know that what I told you here, that this insulation over here is about energy efficiency and it's about comfort for our occupants. This insulation here has absolutely nothing to do with efficiency or comfort. It is solely about durability. So all we're doing here with this insulation is protecting the footing from that upward force. So we want to make sure that we don't let the ground freeze underneath our footing. And that's what that insulation does. It protects, it reduces heat loss from the soil right next to our building, so that we're less likely to get ice and frozen ground here that'll push our building upwards. So nothing to do with efficiency or comfort. That is less intuitive for us, because almost always when we're talking about insulation, we're sort of we've trained ourselves to think about energy efficiency and about comfort, but that's not what's going on here. This insulation is about durability. So I hope that makes sense. Now, when you look at this online, if you Google shallow frost protected foundations, you'll get sort of some version of this. What you'll end up seeing is insulation extending horizontally, or it might extend on an angle. It'll track with grade, but it'll be some sort of version of this. It's not always a little bitty foundation wall here. Sometimes you'll see a turned down slab. You'll see different structural approaches to your slab, but the pattern you'll see is the insulation extending horizontally to this effect, to make sure that we don't get frozen soil underneath the foundation. So it won't always look like this when you're looking at it, or you don't have to design it always like this in your career. This is the principle, though, that you're trying to mimic is this. This is the feature that you'll see in common. Now, second thing to note about this is that if we were talking about a real building, and this right now stops being about the AREs. Okay, so up until this point, this is relevant for your AREs. What I'm about to say, we're going to spend about 5 minutes on it, maybe even less, is relevant to your actual career. So if you were interested in a shallow frost protected foundation for a building that you're working on, I would not recommend doing it in quite this way. I'd recommend doing it a little bit differently. And I didn't have time to draw that out for you right now. I couldn't find examples of it online. So I'm going to find examples and I'm going to post it on Instagram so you can see some photos of that. What I would prefer to see if I were doing this in real life is insulation that is sloped a little bit, because we do get water in the ground, right? It'll rain and water will come down through this and it'll hit our insulation. And what happens when insulation gets wet? Think about that for a minute. If I were to offer you, it's wintertime now, if I were to offer you a nice down jacket, or a choice of 2 down jackets, one is nice and dry, or I've held it in front of a fire and then a fireplace and given it to you before going outside, that would be a nice thing for me to do. So that's jacket A. Jacket B is the same jacket, but I've put it in the bathtub and I give it to you. I mean, which jacket are you going to want to wear when you go outside? The answer is pretty obvious, the dry one. If our insulation is wet, it doesn't do as good a job of insulating. So ideally in this detail, what we would want to do, or in a detail very similar, is we would want to protect this insulation from getting wet. And there's all kinds of ways we could do that with. We could slope this and we could put a layer of, say, polyethylene on top of it and just tape it to the foundation wall to reduce how wet the insulation got. And we could then put the insulation over top of a drainage mat so that the water that does get through it can drain away, or we could install it over gravel instead of soil, like we've got here to facilitate drainage. So if this were a real project, that's what I would recommend. Or say, I mean, this is just ground up here, but let's say we had concrete, like a sidewalk or something, or a patio or whatever. That would do a pretty good job of reducing how wet the insulation got, but I'd still want to install it over a drainage mat. But I hope that principle comes through, right? So this is how you're going to see it. And this is, I guess it must work because we've been doing it a long time, but an improvement over this that I personally would recommend, and now I hope you know the logic behind it, would be to make some design adjustments to keep this insulation dry. And to do that, you could slope the insulation, put some sort of membrane on top of it, and a drainage mat or a gravel fill underneath it. I will post some photos of that on Instagram. It doesn't really matter what kind of insulation you use, as long as it's generally moisture tolerant. So you could use extruded polystyrene, you could use mineral wool, you could use EPS, which is expanded polystyrene. You could, there's all kinds of stuff. Basically anything that you use outside of your wall for exterior insulation, you can use here. And with that, we're like shockingly on schedule. I'm going to open it up for questions, and yeah, or actually we can go back to our original question here, and I'll open it up for questions as well. So now the answer becomes a lot more. Whoops, I'm doing this wrong here. Let's grab my thing. So now this becomes a lot easier here, and you can screenshot this if you want to come back to the logic, but this is our answer here. Our minimum footing depth is going to be 16 inches. Oh, one thing I ought to mention actually before we go to questions is horizontally, how much does this insulation need to extend? And it's typically, follow the code, it'll be in the code, but it's typically whatever the length of where the frost line is, that's how much you want to extend outwards. It's just a rule of thumb. We're dealing with approximations and averages. This is sort of an engineering answer, not a answer of physics, but that usually does the trick for us. So if you're designing for that, make sure that you account for that amount of horizontal room for your insulation. And with that, let's open it up to questions and chat.
So I have a question for an existing building with basement. If we don't know the existing condition, whether insulation was underneath the concrete slab or not, is it a good idea to add an insulation on top of the concrete slab? And where should we locate the vapor barrier or some kind of moisture barrier or weather barrier, I would say, inside, if we don't know what's happening underneath the slab?
Oh, good question. So yes, you absolutely can insulate on top of the slab. And I'm sorry, you said this is a basement condition?
Yes.
Yep, you can insulate on the interior. Unfortunately, when we do that, we lose floor to ceiling height, right? It's a good idea to do it, but often we'll kind of skip that and just insulate at the perimeter or like at the walls, and we'll kind of live with a cold floor. If you do that and you have carpet, the carpet can, because it's cold, can be a host to like mold and dust mites and other not great stuff. So anyway, if you can insulate the floor, it's a good idea to do that. I like to put an epoxy coating down as a vapor barrier first, and over the concrete, and then insulation, and then whatever flooring you want to put down. So that's how that generally works. Let's see. I'm gonna look in the chat here. What about insulation on the outside of the foundation wall? Let me pull up let me share my screen again and pull that up. You know what? I'm just going to share my whole screen, and you can see all my messy thought in my computer. Okay, so you get to see my whole screen. So what about if you were to put insulation, like, could you put this over here? Yes, you totally could do that. But what happens when you do that is you need to do something over here to protect it. And often that is not palatable to us, right? We'll have to put some sort of stainless steel or some kind of cover to get the cut edge of the edge of the insulation that's exposed there. And that ends up being hard to do from a design perspective. But it addresses this, it addresses this, like that's fine. It's totally fine to locate this insulation, to move it from here to here.
Someone was asking if you could just explain a little bit more in depth about how you got to that answer.
Oh, I'm sorry. I guess I misspoke at the beginning and said that the heating degree days weren't relevant, but they actually are. Sorry. Good thing you asked that question. Right here, they're telling us we've got air freezing index 2200 heating degree days. And this tells us, this table from the building code tells us what the air freezing index is. So we know that we're between 2000 and 2500. But we're going to, this is the number of days where it's freezing. So we want to round that up to be safe, right? To be conservative. We don't want to round down, we want to round up. And so we're going to look at this row in our column, the 2500 row, and then it gives us all of these nice things here. What's the minimum footing depth, which is what they're asking us. What's the vertical insulation R value? The rest of this table is the portion that's not relevant. So they're asking us, what is the minimum dimension at that location in inches from grade to the bottom of a frost protected footing? And the minimum footing depth is right here at 16. It gives us that answer in this table. So we talked about the logic of why that is, but this is really just take a look at the table. And in fact, you wouldn't really have to, you could answer this question without really understanding the physics of why this is the case, but it's nice to know why this is the case so that if they ask it in a different way or to actually help you in your career, that's the meaning behind the table. But you could have answered this question without understanding very much about heat loss. You just follow the rules.
Oh, hi, Christine.
Hey, Fred.
Hey, so I'm confused about the answer of the question. Sure. Because the air index day is 2,200.
Right.
When I'm looking at the chart is that 2,200 is between 2,000 and 2,500. So then I was reading the answer as being 14. So that's my first question.
Right. So you were rounding. You're noticing that the answer is or the number of days, freezing days, is in between two things in our table, right?
Yeah.
So I think your question is really, why do you round up instead of rounding down? And or instead of like calculating the average between the two. So the reason that you round up, we know in general that if it's colder in that climate, where is the frost line? Is it going to be higher or lower? So if we're in a very cold climate, how is our frost line going to be? Or let's talk about two cold climates. Let's talk about Toronto and let's talk about Virginia. In Toronto, the frost line, is it going to be higher or lower than in Virginia?
Lower.
So the colder the climate, it's going to be lower, right? So the more of the ground will freeze, the colder the climate is. Colder the climate, the more the ground is going to freeze. So if I'm looking at a table and I want to figure out what my minimum footing depth is going to be, I'm going to want to overshoot the mark. If I don't fall right within the table, I'm going to want to make sure that I make my footing depth deeper, not shallower.
Right. Wrong.
And that's why, so I want to assume if I'm in between, I want to assume that my climate is a little colder than it actually is, not that it's a little warmer than it actually is.
No, I got you. Okay,
so there you go. So that's where it helps to understand what the physics is and like why is this and the colder the climate, the deeper the footing is going to be because we want to put it down below where the ground freezes. It's
safer.
Yeah.
I may have missed this definitions somehow in my history study. But what is the air index? I totally missed that. The 2000.
I don't really know what it is. I mean, so I don't know how they calculate this stuff. I just look it up like everybody else. So it's an indicator of how cold or warm the climate is. So you can Google this for the definition. This is what I would do if I were ever faced with it. But Google air freezing index. I don't think you're ever going to have to know the definition. A similar metric is this one I hear more frequently is heating degree days, and it tells you how many days it's an indication of I'm not going to say it right because it's late and I'm drinking wine and I'm enjoying the company of all of you fine people.
No worry, no worry.
For your
I'll do
areas.
my own search. I have
Yeah,
a very quick question.
but it's a reflection of the climate.
Okay.
It has to do with how mild or harsh the climate is.
Okay, I'll do my own search. I have another quick question. While I was working on masonry stoop and for a house for residential, you know, small sizes, like 100 square feet or something. My question was, do I have to pass the frost line or not? And you know, like supporting a deck with sonotubes and that sort of things, or can we be above the frost line? Because some of the local contractors said, well, we can be above the frost line for masonry stoop. So it was a bit of confusing. And then I looked at the New York building code, and New York building code says that anything smaller than 600 square feet or 400 square feet doesn't have to meet the frost line. So it's sort of like gave me the answer, but I just want to make sure that
it's a great question. It's like, how important is this thing to you, whatever this is? How important is this stoop to you? How big is your budget? And how important is it to your clients? So the rules, it sounds like the rules where you're operating tell you that if something is small enough to not really bother about the footing depth. And that seems fairly sensible to me. So if you have a little bit of slab heave, because remember, there's safety factors in all of these things. And our house is a lot more important than a deck. And so if we have a little bit of movement in our deck, okay, fine, whatever.
Unless the deck is attached to the house.
Yeah, but if it's attached to the house, do we want our deck? Do we want to rip stuff? Maybe if it's maybe that's a good reason to not attach it rigidly to the house. So we get a little bit of movement. Now you can also damage the supports for the deck themselves, and you get a little bit of wonkiness there. But maybe maybe the climate is mild enough, and you want to just roll the dice, and it's not that big a deal. But yeah, that's part of the reason we see all kinds of weird stuff with this isn't the only thing at play, but sidewalks that get all wonky and have to be serviced. So I think the expectation a lot of times is that we maintain those things and we expect to fix them after 20 years, but we don't expect to redo our footings on schedule. I'm guessing as to the logic there, but it's one of those really frustrating things that ends up being a judgment call.
Okay, thank you.
You are welcome. Good question. How about James? And James had some really great, helpful answers in the chat. Thank you, James.
Yeah, no, and actually the stoop question, it's totally analogous to a sidewalk, right? There's a reason why sidewalks don't need to have deep foundations, right? It's just sort of expected that something like this is going to heave over time, and it's factored into the life cycle cost of the building. So you might have to replace a stoop after X number of years.
Well,
I'm curious.
Some people will factor it into the life cycle costs. Other people, certain clients would be extremely annoyed. So it depends on what you're working on.
Right. So I'm curious if you have additional details. So you had mentioned turn down slab. So like, can you show some details for other types of construction besides a stem wall footing? So like a monolithic turn down slab, for example.
No, but I can draw one right now on this bill. Okay, so you've got a turn down slab. Let's say we're insulating it on the exterior. So I don't know why we're insulating it on the exterior, but we are. You end up having to go horizontally out like this and grade. So you end up having to, there's like 1,000 variations of this though. So I've got insulation here and I've got insulation here. And you end up, if you just Google, in fact, I will Google it right now and I will share my screen.
So I've seen the detail like that with the insulation on the outside of the slab, and I don't want to do it for a number of reasons which you pointed out, and also for aesthetic reasons. So is there a way to, I know you need a thermal break or you need something in there so that the slab isn't losing heat out the side. And so if you've got a monolithic slab with a turn down footing, there's not going to be a break, right?
So here, hold on. I'm going to share my screen so that everybody else knows what you're talking about. And then I'm going to show you, I think, an alternative. So this from Fine Home Building, they've got great details at Fine Home Building is what we're talking about. So a simple turn down slab here. We're insulating on the exterior and on the interior. And this is allowing the little wing that allows us to be shallower. But the question is, if we don't want the insulation on the outside, because we've got to now cover this, we have to account for this. Is there a way to do this with a turn down slab? I mean, not really a great way. You can insulate on top of your turn down slab. And so I suppose that would work if you insulate on top, and you'd end up having this sort of wing wall here, but then you end up with some sort of, you've got to figure out what you're doing here with a thermal bridge. So the simple turn down slab is it's a very difficult one to work with when you're trying to also deal with this shallow frost protection stuff.
Right. So maybe the stem wall is just the better option.
Yeah, I think probably it will be. I haven't spent as much time thinking about it as you have. So there might be some sort of magic approach, but if just some way to make the geometry work. Oh, you know what? Oh no, it does the same thing. Let me show you. Oh, okay. There's a book that my computer's on. And this one has a shallow slab protected, a frost protected foundation in it that I will open. This is a great way of learning, by the way, books. You can do this. This is extruded polystyrene, but you can do it with mineral wool too. Now it's on the outside. You could lose that piece, you could lose this piece if you really wanted to. What it would mean is that you would experience heat loss at the side of your slab, but that would be a comfort, that would be an occupant and a comfort issue and an energy efficiency issue. It would not be a slab heave issue.
Right. Cool. I've
So
not
if you
seen
do that,
that detail.
it would
That's
be
interesting.
it'd be a trade-off. So anyway, it's trade-offs. I wish in design that we didn't have to contend with them, but I guess that's what makes design interesting too, is dealing with the trade-offs.
Yeah. Thank you.
What book is that?
Title of
It is
book? Yeah.
so Moisture Control for Residential Buildings. Joe Stebrick, and he's my dad. He wrote it, and it's a fantastic book. It's got really, really great details in it. You can get it. I don't think it's available on Amazon. I think you have to go on their website to get it. So it's buildingscience.com. And they sell books on the website. It's a really great one.
Thank you.
Moisture control. It's in the thing. So I'm gonna cut it short. I'm sorry. I know there are some more questions, but today I gotta cut it a little bit short. But take a look on Instagram to see a more disciplined sharing of the same information on Saturday. And if you want, you can drop a question in the comment section on Instagram, and hopefully I'll get to it then if I can. Obviously, since I can't reach you now. So thanks and good luck on the AREs.